Okay, welcome, gentlemen. I think we're just gonna go ahead and get started, and we'll let people in as they arrive. I hope everyone is doing well. It's a beautiful day here in the A. All right. Hopefully, you're able to enjoy this weather on some level. It's important, do what you got to do academically, but be sure that you got to balance that. I was about to start cussing, but you definitely got to balance it. All work and no play, is no good, right? Let me see. So this is the end of week 10. Just for your awareness, be aware that in week 12, we want to have exam 3 over chapter 2, right? So there's going to be 3 sections in chapter 2, 2.1, 2.2, and 2.3. We finished out 2.2 on Monday, right? So I think we had to use my channel because I think in class time we only have 50 minutes, but it took me like an hour and a half to do it. So you have to go and finish watching the video, take notes as if you're in class to get the full effect. And so today what we're going to be doing, we're going to be making our way through as many homework questions from 2.2 as we can. And again, just as a reminder, if I just go through the questions as many as I can because people don't request any. But if you request a question, we can talk about it. We don't have to do the ones that I'm working on. Okay. Let me get this student. This one. Okay. All right. So with that, yeesh. Let me get this student. JK right there. All right. So let's hop over to Pearson. And let's see. That looks good. And Pearson is here. Let me get this student. And again, if you have questions, I monitor the chat. So, feel free to either type in the chat or, just use the notification. I use that stuff. All right. So this is section 2.2. This is question number 1 from the homework, right? Let me get the student. Yeah, let's start off with the homework, right? Because there are other questions that we can work on as well that could pop up. But I think the homework is a great place to start. And also, I'm gonna go ahead and suppress my audio just so I can focus, because the pings and dings are like distracting for me. Ooh, breaks. So I'm a little bit awkward because I want to say you guys' names as you show up, but I try not to say you guys' names just because I'm streaming live. Let me get my pen ready. Okay. Also, in the chat, are y'all gonna do anything for Halloween? Like, do y'all dress up at all? I have one costume that I've been wearing for years. I need to either make another one or get another one. I have this. I go as a leaf ninja from Naruto. I haven't watched Naruto in some time. I was making my way through Boruto, but I couldn't stand it. I made it up until where Boruto finally acknowledged Naruto's abilities and power. He stopped treating him like some punk, and then I stopped. I was like, I can't watch this. So I think for me it would be better, and I'm kind of stalling because I'm taking attendance. But I think I would do better with Naruto and the animes if all the episodes are released, so then I can binge it. I think I've gotten accustomed to binging things. When I actually have to wait, I can't do that anymore. When I was growing up, it was next time on Dragon Ball Z. That's what it was that I experienced, and I was used to it at that time, but not anymore. Okay, so I think we got everybody present and accounted for. Let me make sure. Let me see. The audio looks good. Okay, let's go ahead. So again, this is question 1 from the homework. This comes from section 2.2, question 1. So with this section, again, what we're talking about are polynomial functions. To recap what we talked about, some of the concepts on Monday, we talked about the leading term test. It's telling us about the long-term behavior, how to identify a polynomial. For instance, if we look at this one, it says consider this polynomial. Let me see if I can make it a little bit bigger. Let me see, was it like this? Okay, I think that's a little bit better. So consider this polynomial that you see. It says write the degree of the polynomial, the leading term, its leading coefficient, and the constant term, right? So this is basically a question on terminology, right? Okay. So we're giving it as a polynomial. First thing is I just want you to recognize that this is a finite sum of monomials. Again, a monomial is, let's see, okay. A monomial is basically, it's like a variable raised, let me get the student too. I keep pausing because I'm taking attendance as students pop into the queue. But a monomial is basically a variable raised to a non-negative integer exponent times some real coefficient, right? Again, non-negative. For a moment, I want to ask you this question: like, do you know the difference, or can you identify what's the difference between non-negative versus positive, right? What's the difference between non-negative versus positive, all right? Positive, I mean, I think like non-negative non-negative integer versus a positive integer. I think positive, numbers greater than 0, right? So then non-negative are still numbers greater than 0, but now we can include 0. So non-negative means not negative, right? It's all in the. Let me get the student. Right here. All right, let him in. Okay. So it says, consider this polynomial, right? Finite sum of monomials. Write the degree of the polynomial. Man, everybody's like popping in one by one. It's all good though. Okay, I think we're past the bulk of it. So the degree of a polynomial is going to be the highest exponent on any variable, right? The degree of the polynomial is going to be the highest exponent. So in this case, the degree, hopefully you got it by now, is 5, right? So that's just some terminology. Let's go to the next one. The leading term. The leading term is going to be the term that has the highest exponent, right? So terms are things that we add and subtract. Factors are things that we multiply and divide, right? So the leading term is the term with the highest exponent. That's going to be this 2x to the power of 5. Okay, let me get this student. Boom. Let him in. Okay. The leading coefficient. So the leading coefficient is going to be the number in front of the leading term, right? So the leading term is 2x to the 5th, so the leading coefficient is 2. Okay. The constant term is the term that has a degree 0. It's like, basically it's just the number with no variable. So that's going to be the -6. All right, so that's just some terminology. Okay. Again, like mathematics, essentially you know this stuff. Like I know it can seem intimidating because it's information overload, but this is like, even though this is college algebra, this is really a language class, right? Because then once you understand the language, like non-negative, constant, these kind of the jargon, then once you understand the jargon and you know what you're looking for, then it makes things a little bit easier. For the following polynomial, find the degree, leading term, and leading coefficient. Okay, so we should rewrite this, right? We should distribute, because we're dividing by one term, we're divided by a monomial. We should essentially distribute that 5, right? It's really distributing a 1/5, but so this is really 2/5. 10 divided by 5, this is really a 2, right? So the degree is going to be the highest exponent on any term. So the highest exponent is 4, right? Okay, they trying to get us a little bit. See, okay, do we really know the terminology or not? The leading term of the polynomial is the term with the highest exponent. So, and remember, we need to distribute this 5 because we're divided by one term. We can distribute it. If there were 2 or more terms down here, we can't do what we're about to do. The leading term is going to be 2/5 x to the 4. 2/5 x to the power of 4. Come here, come here. The leading coefficient is going to be 2/5. Come here. Come on. Come here. Lay down. Right there. Come on. It's okay. Here. You got some sunlight. Right there. All right. Let's go to the next one. Following polynomial, find the degree. Okay, we got a real coefficient, non-negative integer exponents. Find the degree, the leading term, and the leading coefficient. The degree is the highest exponent on any variable. That's going to be the 3. So the degree is 3 here. I felt like one of those auctioneers. Oh, okay, we got a polynomial. You got the highest, it's gonna a 3, and that's what it felt like. Anyway, the leading term of the polynomial is the term with the highest degree, so that's going to be the pi x to the third. Let's see. So if we hit pi x to the power of 3, boom, awesome. Leading coefficient is the coefficient in the front, so that's going to be pi. Oops. Like this. Okay. Cool. Let's see, we're looking like cool beans. Okay, explain why the given function is not a polynomial, right? It's basically this absolute value term, right? If we were to graph that, it would cause like a sharp edge or a corner at some point because of the absolute value. Yeah. Nope. Right here, B, right? The function is not a polynomial because of the presence of the absolute value. Yeah. We're going to go B. Okay. Determine if the following function is a polynomial. I would say no, because even though we could like distribute, nope. Even if we distributed that x squared, right, and like divided it out, this term would become 1, but then this would be x to the minus 2. Remember, the exponents have to be non-negative integer exponents. On top of that, with this x being in the denominator, that would cause us to divide by 0, right? If x is 0, then that means there's an x that's unaccounted for. Therefore, the domain is not all reals, and one of the properties of polynomials is that the domain is all reals. It's not a polynomial. Okay, let's go with that. So there's a couple of reasons. I mean, you can say because the domain is not all reals. There are a couple of properties. Let me get the students. Cool, got him. Got him, coach. Let him in. All right, explain why the following function is not a polynomial. This first term is fine. This cube root of x squared, that's the same as x to the power of 2/3, right? So remember, polynomials, the exponents have to be non-negative integer exponents. That's a rational exponent, because you can rewrite the cube root of x squared. You can rewrite it as x to the power of 2/3, right? So that cube root has a non-negative integer. It's not a non-negative integer exponent. Yeah, because of this, the radical here. It's a. I'm just going to go with A. Okay, let's try another one. These are interesting questions, actually. Is the graph of a polynomial? No, you have an asymptote, right? You have a huge gap. There's a gap or a break there, right? So that's going to be a no. Remember, the main two properties of the graph of a polynomial graphs are continuous. So that means you can start from any point on the graph and get to any other point by tracing the graph without picking up your pencil. With this one, if we try to trace it, we would have to pick our pencil up to get across that gap, right? So is it a polynomial? We're going to say no. Okay. Explain why the given graph cannot be the graph of a polynomial. Let's see what we're working with here. Yeah, we got a huge gap. Because it's a curve, no. The function is not a polynomial because the graph is continuous, no. That's not why it's not a polynomial. Again, continuity is a property of polynomials. The function is not a polynomial because the graph has a straight line, no. The function is not a polynomial because the graph is not continuous, yeah, D. Okay. Match the following polynomial function with its graph. Okay. So some properties right off the rip. With this form, I want to say the y-intercept is -1, right? Notice that the leading coefficient, oh, okay, yeah, we got it right there. So the y-intercept, right? Basically when x is 0, y is going to be -1. That's why I like to do the y-intercept first. Let me get this student. Because it's oftentimes much easier to find the y-intercept than the x-intercepts. Because when x is 0, it cancels out a lot of the terms, all right? Y-intercept, you can almost just look at a lot of these formulas or equations, a lot of these functions, and see the y-intercept off the rip, okay? Now, let's do the leading term test and talk about the end graph behavior. Notice that the leading term or the leading coefficient is negative, that means the graph should go down to the right. It should fall to the right. And because the degree of the polynomial is even, the other side does the exact same. So it should go down to the right and down to the left, right? Let's do, I think it's like this. Let's try to change this view a little bit. Okay, we said it should go down to the right and down to the left. Say we weren't sure, you can put that in your graphing calculator, all right? And if you don't have a graphing calculator, especially because this is a remote course, you can use sites like GeoGebra, which is like GeoGebra, geogebra.com, or I think it's Desmos.com, and those are like free online graphing utilities, right? They're free. So even if you don't have a Texas Instrument, you can at least look at the graph. You just have to, I would do a Google search for free graphing software. And then it takes a little practice to actually use those things. But once you get used to it, I mean, it's free. And it's an invaluable tool that you can use, throughout your college career and beyond. But let's go with B. And just stop me if anything is not clear, if you have questions about anything. Let's go on to the next one. Check something really quickly. It's looking good. Okay. So since that didn't change, we can do, is it like this? Okay, that's too big. Okay. Okay. So again, y-intercept is 7, so it definitely can't be C, because that y-intercept is definitely not 7, because that's almost to 30. It can't be D either, because that's the wrong y-intercept. If we look at the leading term, notice the leading coefficient is positive, so that means the graph should go up to the right. And then the degree of the polynomial is even, which is 4, which is even. So that means the other side does the exact same thing. So it should go up to the right and up to the left. So it would have to be either B or C, but again, we already ruled out C because it has the wrong y-intercept. So then it should be B. B is the only one that fits those criteria. Right? So like that's kind of how that goes. Let's do it some more. Match the following polynomial with its graph. What's the y-intercept? Again, you can look at it right off the rip. What's the y-intercept? Y-intercept is when, if you set x equal to 0, all right, you should be able to look at that and get the answer. Boom. Okay, almost no thought. Okay, so now if we know we have a y-intercept of 15, so it can't be B, it can't be C. It could be either A or D, right? Those are the ones that have a y-intercept of 15. So then if we do the leading term test, the leading coefficient is positive, so it should go up to the right. But then the degree of the polynomial is 3, which is odd. So that means the other side does the opposite. So it should go up to the right and down to the left. The only one that fits those criteria is D. Okay, we are like moving and grooving through these. Yeah, it's not that many questions. So what I'll probably do is, like, if we make it to the end of the homework, I'll go back and like try to pull on some questions that, because the homework that I assign is not all the questions, right? So, but when I create your exams, what I've been doing is I'll take all the questions from whatever sections and then pool them, so that, and put them into a pool or group. So then what that means is that there are some questions that could pop up on the exam that were not exclusively in the homework, right? But you can definitely get them. You can solve them because it's the same content. Let's see. For this polynomial function, so if we finish the homework, I'd like to go back and see, can we find some of those questions that could pop up on the exam that's not necessarily in the homework. For the polynomial function below, list each real zero and its multiplicity to determine whether the graph crosses the x-axis or touches and turns around at each 0. Okay, oh. Now see, when it said find the zeros, I was already gearing up to get ready to factor this thing, but the math gods were smiling favor on us today because this was already factored, so we didn't have to factor. So honestly, in this form, you can just look at it and write the zeros, right? If we want to find the zeros, we would set this thing equal to 0. And then, so if you set this function equal to 0 and solve, you would use the zero factor property, because when you have things that multiply to give you 0, then you basically just set each thing to 0 and solve, right? So the zeros, if we set this factor to 0, the answer will be 4, right? Because if you plug in 4, that's going to make that 0. So we're going to say 4 if you set this to 0 unsolved, you would take the square root on both sides and then subtract 3. The answer would be -3 there. Okay. Okay, that looks good. I think that's it. And then the multiplicity. So the multiplicity of 4 is going to be the exponent on the binomial, right? So this binomial, if there's no number written, there's an implied 1 here. I don't know if you can see my cursor or not, but if there's no number written, there's an implied 1. So the multiplicity is 1, okay, for that one. And then the multiplicity of the -3 is 2 because it is squared. So that multiplicity is 2, okay? So then at 4, because 4 has an odd multiplicity, that means it's going to cross the x-axis. All right, because 4 has an odd multiplicity, it's going to cross the x-axis. Because the -3 has an even multiplicity, it's going to basically bounce off the x-axis. It's going to touch and turn around. Okay. We're moving and grooving. For the following polynomial function, find the zeros and its multiplicity, state whether the graph crosses or touches. What's the max number of turning points? Okay. So again, we were fortunate with this one because it's already in factored form. So, you know, the simple thing is basically the opposite sign, right? Because if we plug in 8, it's going to make this 0. So the first 0 is x equals 8. Okay, and then -1, right? Because it's the same argument for the previous, right? For the previous example. I think those are the only two. The multiplicity. So the multiplicity of 8 is 3 because of the exponent, right? Hopefully you guys are paying attention, you know, because I know you guys, I know how it goes. I mean, you know, I don't really know like what you experience because I never had to like do an online class, especially something like math, right? So I try to be considerate like with my presentation and delivery and the structure of my class. The multiplicity of -1 is 2. You know, so I don't really know what you guys experience. I'm not really, I'm just kind of tailoring towards like, I kind of drawing on some techniques that like my favorite professors did as far as certain things. They just helped me. I felt like it helped me anyway. It gave me like confidence to keep going. So I just try to do something similar. State whether the graph crosses or touches. Okay. So at 8, right? Because 8 has an odd multiplicity, that means it's going to cross the x-axis. Because the -1 has an even multiplicity, it's going to bounce. It's going to touch, turn back. Maximum number of turning points. So the maximum number of turning points is going to be the degree of the polynomial minus 1, right? So first we need to find the degree of this. If we were to expand this all the way out, eventually we would have an x cubed times an x squared to give us an x to the power of 5. So if the degree of the polynomial is 5, then we have at most 4 turning points. And the way I kind of remember that, if you think about like a quadratic, a parabola, right? A quadratic is a degree 2, and it has at most 1 turning point, right? It has at most one turning point. So then that's how you know. So with that, I know that going forward, the most number of turning points is the degree minus 1, n minus 1, basically. Determine the zeros of the polynomial function and their multiplicities, then decide whether the graph touches or crosses, so the same kind of deal. Now this one, it looks like we need to factor some, right? So they got a GCF factored out. We were looking two numbers that multiply. I'm just going to type it here. I'm not going to write it out exclusively. I'm just going to type the factor form. X to the power of 4. Now I'm looking for something that behaves like this. I just got to be sure not to hit enter. I know it's going to be x minus and it's going to be x plus. I'm looking for two numbers that multiply to give me -2 and add to give me -3. I think it's -2 and +1. -2 and +1, right? And that setup, because the second sign is negative, I knew my signs were opposite. In order for them to multiply to give me a negative, my signs have to be opposite. This first sign tells me that the larger number is negative. Because this is negative, that means my larger number is negative. So that's why I said -2 and a +1. And then quick check. Notice that -2 times 1 is -2. No, this isn't right. Right? This doesn't work. because -2, so maybe you can't factor it, because I think the only factors are -2 and 1. So I think if we tried to solve this, now we could use quadratic formula, but I think we're going to get like a non-real solution from there. So I'm gonna kind of, without putting in the quadratic formula, I'm just going to say you can't get a 0 from there. So the only 0 I see is 0. Like basically, if you set this first thing to 0 and solve, you get 0. This one, if we use quadratic formula, b squared minus 4 times a times c, 9. Oh, wait a minute. Okay, yeah. I'm getting a little ahead of myself. I think I am going to need to write this one out because I think we do need to use the quadratic formula. So let me take some notes real quick. I'm glad I thought about it. I'm moving too fast, basically. Let me write this one out really quickly. Okay, so this is question number 14. This comes from section 2.2, question 33, right? I'm just going to say find the zeros. Okay, we have f of x. I'm just taking some notes and we'll hop over there. Equals x to the power of 4. We got this x squared minus 3x minus 2. Okay, let's hop over to the tablet. Let's see, like this. That looks good there. This one, and let's do like this. Okay. Let me see something else. Okay. So these are the notes that I just took, and we're basically asked to find the zeros. Right now, notice I tried to factor that second part, but it didn't work out when I checked it, right? We got the -2, but when we added them, they added up to -1 and not -3. And so 2 and 1 were the only factors to consider. So we couldn't factor it that way. But then I was like, well, maybe we can use the quadratic formula, right? So I'm going to share a former student of mine, the way he remembers the quadratic formula. Hopefully, it's a little bit non-PC, but that's just how I remember it. Ever since he showed it to me, he told me this, I couldn't not think of it that way, right? So the way the student remembers the quadratic formula is in the following, right? The negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m., right? So that's how I remember it now because of that. Like it's like Hangover. It's like a little movie to me, right? And that's honestly one of the memory techniques. Like if you're just doing like rote memorization, you kind of, whatever it is you're trying to remember, you associate it. It's called like a memory mansion or memory palace, where basically whatever it is you're trying to remember, you associate it with the more zany the image, the easier it is to remember, right? So if you're trying to remember something, you just associate it with a zany memory. So I wanted to remember this formula, so it's basically like a little movie reel for me, right? So then let's identify our a. So if we're applying the quadratic formula to the quadratic, in that quadratic our a is 1, our b is -3, and our c is -2. Let's plug this into the quadratic formula and see what happens. All right. So then we're going to get x equals, so negative here, let me do like this. Negative b plus or minus the square root of b squared minus 4 times a times c. So first thing that I'm doing is replacing each of those components by blank parentheses, right? And then what goes into the blank parentheses? All those numbers that we found. So negative b, so b is going to be -3, -3 squared, a is 1, c is -2, and a is 1, right? So again, when I plugged it into the quadratic formula, I replace each component with a blank set of parentheses, then I plugged those numbers into the blank parentheses. And what the blank parentheses do, they help us to keep track of the negatives. Without the blank parentheses, it's very easy to lose track of those negatives and you'll be led astray. Okay, so now let's keep going and account for some of these changes. So first, right off the rip, we got a double negative, right? So that becomes a +3, plus or minus. -3 squared is the same as -3 times -3. So double negative is positive, so that's going to be a 9. We got -4 times 1 times -2. So double negative is positive. 4 times 2 is 8. Okay. And then over 2, right? So then I think we get the exact result. We get 3 plus or minus the square root of 17 over 2, right? So these aren't all the zeros, but these are the zeros that we were about to miss. Like if I had submitted x equals 0 without plugging into the quadratic formula, this is what we were going to miss out on, right? So this in addition to 0. Okay, so let's hop back to Pearson. Okay, so the zeros. Use commas to separate. Type an exact answer using radicals as needed, right? So we got the 0, then we got, let's do a fraction. Nope, let's try that again. Comma. I want it to be kind of like this. Yeah, that's what I want. 3, let's do minus the square root of 17. 3 minus the square root of 17 over 2. And then comma, we want 3 plus square root of 17 over 2. Okay. These are the zeros that I get. Okay, my ears are ringing. That's all good. We got like a solid maybe 15 minutes. The multiplicity of the 0 located to the farthest left. So 17 is just above 16, right? 16 is a perfect square. So this number is a little bit bigger than 4. So that means this thing is negative and this one is positive, right? So the one to the far left, the multiplicity, so this one has a multiplicity of 1. So that one's going to be a 1. Okay. So the center one is the 0. The 0 is x to the power of 4, so its multiplicity is 4. And then the far right is a 1. Okay. So the leftmost, so because it's a 1, it's going to cross the x-axis. The middle one, because it's even, is going to bounce off the x-axis. And then the far right is going to cross. Okay. Boom. Okay. They almost got us with that one. Almost. You know, but that don't cut it. Almost don't cut it. Use the intermediate value theorem to show that this polynomial has a real 0 on this interval. Approximate the 0 to 2 decimal places. Okay. Let me think about it. So the intermediate value theorem, because we're working with a polynomial, once we show I was gonna say once we show that, like, okay, if we plug in 1, we show that the y values of the endpoints have opposite signs, and there has to be a 0 in there. Think about something, because I'm tempted to just put this in my calculator to find that 0. I want to see the way they want you to do it though without the calculator. Let me go view an example before I just jump to the calculator. How do I get to the next part? Okay. Blah, blah, blah. Yeah, so they're showing the opposite signs if they plug in the endpoint. So they got a negative value and then a positive value, right? So then there's a 0 on the interval. Okay, so I think they're just choosing test points, right? So they're making a table. So then they do a table. We could do this with the calculator. I mean, you can do it way faster though, if you're going to be using a calculator. So, for instance, they started at 1, then they did it in powers of 10, right? And then they see the sign change occurs for this one between 1.7 and 1.8. So then you come back and do a second table where you do 1.71, 1.72 until you get to 1.8, right? So then you can see a sign change between 1.7 and 1.8. But that's just a reiteration of the intermediate value theorem. Okay, so for our case, let's hop back over to the tablet. We can honestly do what they did, and we can do it quickly. There's 2 routes that I'm seeing here. So let's hop over to the tablet. Go like this, like this. Okay. Oh, so you guys can't see it. Okay, let me take some notes real quick. Let me at least get a copy of this because I was gonna do something, but let's see. This is question 15. I'll show the quick way. Let me duplicate what they did first, and then I'm gonna come back and show a faster way. If you're using a TI 83 plus, right? So this is 15. This comes from section 2.2, question 35. I'm gonna abbreviate it as intermediate value theorem. All right. We have p of x equals 2x to the 4 minus x to the 3 minus 14, right? Okay, let's hop back over here to the tablet. We can hide all this other stuff. Okay. Oh, and I think the question also says show it has a 0 between 1 and 2. Okay, so now let me break out my Texas Instrument, my graphing calculator. Let me finish my attendance. So I'm gonna hit absent. So guys, just be careful about coming in late. I mean, it hasn't been rampant, so that's why I hadn't been making a big deal about it. You know, and I kind of been in a good mood, so it's just like it's okay. For now, let me see. I'm looking for this guy. Okay, that looks good. Refresh and reload, and awesome sauce. Okay, want you over here. Okay. What time is it? We got a solid 10 minutes. Okay. So I'm gonna go to my y equals, and let's replicate what they did, right? So if we put in 2x to the power of 4 minus x to the power of 3 minus 14. Hopefully I didn't make a mistake there. Okay. So then next thing I want to do, so in the upper right hand corner of the calculator it says graph. Before I click on table, which is the yellow part, to the left where it says window, above that it says table set. I'm going to click second window, so I open up the table set. I want the table to start at 1, and I want it to change by 0.1, right? So I'm setting the parameters of the table. So now if I click on second graph to open up the table, it starts at 1, right? Notice we got a negative value, and then let's see if we can see the sign change before we get to 2. Boom, right there. So between 1.7 and 1.8, we get a sign change, right? So then what we want to do is go back to table set. We want it to start at 1.7, and we want it to change by 0.01. Now, when we go back to the table, it starts at 1.7. Now let's see if we can see the sign change again. It said 2 decimal places. So there should be a sign change between 1.7 and 1.8, and there it is right there. If we want 2 decimal places, let's do it one more time. Let's have it start at 1.76. So I'm going to go to table set, start at 1.76, and we wanted to change by 0.001, right? We're going a little bit further in just to get so we can get it to 2 decimal places. Now we go back to the table. We're starting at 1.76, and notice, we get our sign change right there, all right? So between 1.767 and 1.768, both of those round to 1.77. So we'll say approximately 1.77, right? Because 1.76, 1.767 and 1.768, they both round to 1.77. So we're going to go with 1.77, right? So let's hop back to Pearson. So we got 1.77. So 2 decimal places is needed. Let's go 1.77. Cross our fingers. Awesome sauce. All right. We should have time for at least one more. Use the intermediate value theorem to check whether the polynomial function has a zero. Oh, I wanted to show you. Okay, maybe I'll use a shortcut for this one, right? Because I didn't show it for the last one. Okay, so this is what, question number 16. I'll do the shortcut on this one. Question 16. This comes from 2.2 question 37. I'm going to say intermediate value theorem. We have p of x, the polynomial, equals 2x to the power of 5 minus 3x squared minus 12. We want to show that it has a 0, let me see, between 1 and 2, right? On the interval from 1 to 2. Okay, let's use a shortcut for this one. Now we could go back and do the same technique that we just did, right? But let's do the shortcut for this one. So now we're going to go to my y equals, clear out that old one, and put the new one in, 2x to the power of 5 minus 3x squared minus 12, okay? So now I'm going to hit graph, right? I think this is already in standard form, and you know, it's not a good view of the graph because we don't really see it, but we can see the 0 is between 1 and 2, right? So then I'm gonna hit second calculate, or when you hit trace, it takes you to calculate, and I want to find the 0. So number 2. It says a left bound, so x equals 0. Yeah, I just want to be left of 1, and then right of like 2, or basically right of that 0. So I'm gonna just keep clicking to the right. I know I'm to the right of it now. So I can go a little bit past 2, right? I'm gonna hit enter, and then I guess I want to get as close to the 0 as I can. That's about as close as I can get. Now when I hit enter, that's the shortcut, right? So this is saying that the 0, it has 1.576. The 6 rounds the 7 to an 8. So we're going to submit 1.58. So let's hop back to Pearson. Let's submit 1.58. 1.58. That was a shortcut. We still got time for another one. How many more? We did 16. We're almost at all 20. For this function, answer the following. Describe the end behavior. Okay. And then sketch the graph. So the end behavior. So the leading term test is this x to the 5, right? So the leading coefficient is a 1. So that means it is a positive 1. The leading coefficient is positive, so the graph goes up to the right. Then the degree of the polynomial is odd, so the other side does the opposite. So it rises to the right and falls to the left. Let me see. Falls to the left. Nope. Nope. Wait a minute. Falls to the left. No, and no, it's not. Oh, it's another one. I was like, none of those are right. I was like, what's going on? It falls to the left and rises to the right. D. D is the one that we're looking for. Okay. Okay, so the y-intercept here, notice there's no constant term, so the y-intercept is 0. So it should pass through the origin, rising to the right and falling to the left. Let's see. Pass through the origin, rising to the right and falling to the left. So it can't be A, that's not behaving the right way. It's not B, it could be C. The only one that rises to the right and falls to the left is C. So we're gonna go with C. Okay. I think we might have time for another one. This will be the last one. For this function, answer the following. Describe the end behavior. So you might be tempted to say negative 8x squared, but we need to expand this some more, right? We need to get it in the general form, right? So if we distribute this 8x squared, we're actually going to have a negative 8x cubed. If we distribute, right? We got to distribute. So because the leading term is negative 8x cubed, that means the leading coefficient is negative 8, which is negative. So that means the graph falls to the right. And because it's cubed, that means the other side, the degree of the polynomial is 3. The other side does, which is odd, so that means the other side does the opposite. So this falls to the right and rises to the left. Rises to the left and falls to the right, so it should be C. All right, so the trick there is that we needed to distribute the 8x squared and expand this all the way out first. Okay, all right. So let me go paper. I probably won't share these notes because we didn't write that much. Let me put this back. Okay, and let's hop back over here. So I can't really think of any other announcements. Hopefully that was okay for you guys. But on that note, if there aren't any burning questions, we're actually going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. All right, guys, take care. Peace.